In recent years, power usage has increased exponentially. So planners have been looking at new technologies and ideas to help bring us out of the 20th century mode of power generation and into the future. Not surprisingly, NASA personnel are part of the core wave of engineers and researchers who are looking at ways to change how we develop power. While some of their ideas will have Earth applications, the bulk of their study is finding ways to improve how power is used and developed aboard spacecraft. This work will help us move past our current methods of power generation in space, allowing new and exciting technologies to come online that could be the disruptive force we need to advance spaceflight. Coming up on this episode of NASA X, we will follow researchers from NASA's Space Technology Mission Directorate's Game-Changing Development Program as they attempt to transform the way spacecraft of the future are powered. We will see how these changes can increase speeds, be more efficient, be a fraction of the size, and potentially cost much less than conventional methods. And with these new technologies in place, they could have the potential to move us even closer to the goal of exploring deeper parts of space. Since the beginning of spaceflight through today, there have been huge improvements in the technologies surrounding vehicles that travel in space. As an example, the flight computers that flew humans to the moon in the 60s and 70s were state-of-the-art then, but had less processing power than a cell phone of today. In the more than 40 years since Apollo, there have been enormous changes in every aspect of spaceflight, not the least of which is in the fields of power and propulsion.
Main engine ignition. 4, 3.
Often these fields get overshadowed by flashy mission hardware and instruments, but without these core elements in place, no mission would ever make it off the ground. Because power and propulsion are so important, NASA's Space Technology Mission Directorate is taking steps to continue improving our understanding by ensuring that next-generation technologies will work as expected and help move us past our current methods of travel. They have broken power and propulsion up into two major categories. The first is in the field called in-space propulsion, which refers to the development and testing of different types of thrusters that are used in space, while the second area is called space power, which studies how power is generated on orbit, such as solar arrays, for example, and also how we store energy with batteries and fuel cells. To understand what future missions will be like, we first have to look at the space environment and how missions of the past have worked. Because of Earth's gravity and atmospheric conditions, we still need those big, powerful rocket engines that burn chemical propellant to get us into space. Once in space, current missions and those of the past mix an oxidizer with the chemical propellant for a short but powerful push toward the given destination. This burn lasts only a few minutes, then shuts down. Because the craft is not fighting gravity or atmospheric conditions in space, it just coasts the rest of the way without losing any velocity. Although this practice still works well, researchers in recent years are looking into new ways to get to destinations. One of the most intriguing ideas on the table is something called solar electric propulsion, or SEP. Helping to lead this effort for NASA's Game-Changing Development Program is Principal Investigator Chuck Taylor.
The new idea is what we're really focusing on now is electric propulsion. And that differentiates itself from chemical propulsion in that rather than combusting a fluid and getting a managed explosion, if you will, you're basically exciting ions and getting an electron and an ion stream leaving the end of the engine, and that's how you get your propulsive force.
This form of propulsion is intriguing because it uses energy captured by the sun. It relies on the acceleration of ions using electricity generated by solar arrays instead of the chemical energy stored in the propellant itself. It is very attractive to NASA planners because by using the sun's energy in the process, considerably less propellant is being brought into orbit, which reduces launch mass and cost. An SEP system is usually considered to consist of the large arrays that generate electric power, the power processing units that convert this power, and the thruster, which uses the electric power to ionize the inert propellant and accelerate it out of the spacecraft to generate thrust. Each of these elements are being studied, with one of the most important pieces being the large solar arrays themselves. A big challenge facing planners is how to get enough power to complete missions.
We're creating a set of solar arrays that are about 2 times the size of solar arrays that are in use today. We're talking about generating on the order of 50 kilowatts of prime power, which was a substantial step up from what is used in commercial industry today or any government satellite. The biggest hurdle we have to overcome is the mass of those arrays and the stowage volume of those arrays. If you think about it, the space station has arrays that are a rough equivalent of what we're trying to produce, but it took upwards of 10 shuttle missions to get those arrays on orbit, and we had to have astronauts actually go out and put them together and assemble them. We're trying to make arrays with just as much prime power, but be able to be stowed on one rocket launch and have them deployed autonomously.
Because these new arrays are so large and so unique, testing them will take a very special facility. Just outside of Sandusky, Ohio, is one of the most important testing chambers in the world. Called Plum Brook Station, this NASA facility is home to the world's largest space environment simulation chamber. At just over 100 feet wide and 122 feet tall, it is possible for researchers to perform full-scale tests of spaceflight systems in a vacuum and temperature environment ranging from low Earth orbit to deep space and planetary surface conditions. You may have seen this facility before if you saw the first Avengers film. But the real-world applications that NASA is developing here have the potential to be more revolutionary for future space missions than anything Hollywood could think up. NASA's Carolyn Mercer walks us through the facility to explain how next-gen solar arrays will be tested.
This is the Space Power Facility at NASA's Plum Brook Station. It is the world's largest vacuum chamber, and we are going to bring one of our solar arrays right in here to determine whether or not it really is going to be able to autonomously deploy in the conditions that simulate space, namely a vacuum and hot and cold temperatures. Just like a tall ship, we have masts that are going to be used to hold our cryo shroud and booms and spreader bars to attach to the vacuum chamber here. The cryo shroud itself is called that because it is going to be cryogenically cooled to get us to minus 60 degrees Celsius and then warmed up to plus 60 degrees Celsius. This cryo shroud is big. It's 40 feet in diameter, 40 feet high, but it's big enough to hold our about 30-foot diameter solar array wings.
As Carolyn mentioned, NASA will be testing these new 30-foot solar arrays in this facility. Of course, solar arrays in space are not new, having been used for decades to power spacecraft. But if we are to move past low Earth orbit and into deeper space, new technologies like improved solar arrays will need to come online.
Solar arrays are flying right now. Commercial satellites are flying solar arrays. And the International Space Station flies solar arrays as well. For comparison, the new arrays that we're building right now are going to be about 20 kilowatts of power. They'll provide about 20 kilowatts of electrical power. And they're about 100 meters squared in size. So for comparison, for a single solar array wing on the space station, you'll get about half again as much power, so about 30 kilowatts, but it's 3 times bigger, much larger area. And for a commercial satellite using solar arrays, the state-of-the-art is about half the power, about 10 kilowatts. But the important thing is that the state-of-the-art uses rigid panel construction, we call it. So the solar cells themselves are fixed onto like a honeycomb structure. We're not doing that anymore. We have this really novel, flexible blanket technology, so that combined with high efficiency cells and lightweight structures, we can get very large arrays. So for instance, we're building about 20 kilowatt sized wings right now. You put 2 of them on a spacecraft, you get about 40 or 50 kilowatts of power. That will enable you to do exciting missions like the asteroid redirect mission. The very same design can be scaled up to, let's say, 250 or 300 kilowatts, and that would allow us to send people out to an asteroid. And then the same technology can be scaled up yet again to maybe 800 kilowatts, and we can send people to Mars. So I'm really excited about this technology because it is the stepping stone for how we're going to explore space differently. And this matters a lot because solar electric propulsion, for which these wings we're developing, it's a much more economical way to explore deep space with people.
The solar arrays address the solar and electric part of SEP. But what about the propulsion? Here at NASA Glenn, researchers are working on new thrusters that will work in concert with the arrays to power these new devices. Thrusters like these use the electricity captured by the arrays to ionize the fuel, which in this case is xenon, to produce the thrust that pushes the craft forward. Although this technology has been around for decades, the more than 200 satellites already using them only have very small thrusters. NASA needs much larger devices to move us further into space, so there is a big push to build these devices.
Here we have a 12 kilowatt Hall thruster. Hall thruster technology is also being invested in by Game Changing to provide high fuel efficiency, higher power, higher thrust capabilities for in-space propulsion. So this is about the same size as the thruster that's being developed within the Space Technology Mission Directorate, a little bit larger in size. The improvements that we're trying to make by studying these devices is increasing lifetime, an order of magnitude, increasing power, and increasing the exhaust velocity of the ions. That exhaust velocity is a higher specific impulse, and it provides better fuel economy essentially. And what we're trying to do here under the Game Changing is really push on 3 critical areas. The power level, so 2 or 3 times the current state-of-the-art power level. Higher exhaust velocity, 50% higher exhaust velocity results in higher fuel efficiency, and 3 or 4x the operational lifetime. So geostationary ComSats, they have lifetimes for the spacecraft on the order of 10 to 15 years, and that results in a 10,000 hour or so lifetime requirement for station keeping for the thruster. What we're talking about is a thruster that can last 40 or 50,000 hours of operation, so multiple years of operation.
But the thrust is tiny on these types of craft, about the equivalent of the weight of a coin resting on a table. But a major benefit is how long they can burn. Instead of the quick and powerful burn for a few minutes like a chemical rocket, these ion thrusters can burn for thousands of hours, which allows that tiny amount of thrust to build up into speeds needed for deep space missions. But solar electric propulsion can also be used closer to Earth as well. Researchers believe that solar electric propulsion can be used as a type of space tug that can take satellites launched at low altitudes and bring them to higher altitudes, potentially saving millions of dollars in propellant costs. Many believe that solar electric propulsion may also be a viable way to service satellites and remove dead satellites as well.
Satellites are a big industry right now, and when they decay and they are no longer of service, it's you can't just call someone up and have them go out there and service. It's a big deal. Send something into space to fix one, but if you fix it, it can generate a lot of revenue to the companies. So solar electric propulsion is one mechanism we can use to get there and potentially service. So that's another mission concept.
But it also can get rid of the broken down satellites that are cluttering up our orbits, what we call our space debris problem. So there are a multitude of commercial applications in and around Earth for solar electric propulsion.
As SEP technology gets larger and larger, researchers also see a need for thrusters to get even smaller. With that thought, NASA researchers have been working on thrusters, generically called microthrusters, that can make small but precise maneuvers.
We're working with microelectric spray thrusters. Those are basically the size of a sugar cube. And rather than working, trying to push very large spacecraft, asteroids around, we're talking about trying to do a couple things. Provide main propulsion for CubeSats, very small satellites that are now going into use for university research. Other government agencies are using them for various purposes. And to date, they've been launched without propulsion. So we're creating thrusters that actually use very little power and can be used to both provide prime power for those spacecraft, but also attitude control so that you can reposition and point the satellite the way you want to when you have a sensor looking at Earth. These sensors are also so precise they can be used to point telescopes like the Hubble or the James Webb in the future. And by using these types of thrusters instead of our normal way of positioning these systems, we're hoping to greatly reduce the mass of those satellites. Our hope is that in the end, these systems are very, very scalable. I always use the analogy of the plasma screen TV. Rather than having one sugar cube with a very minute amount of thrust in it, I can string an entire flat panel together with many, many sugar cubes and reach a thrust potential close to the types of systems we're building for that asteroid retrieval mission. Now that's many years in the future, but that's what we're hoping we can get out of that technology because of the efficiency in the basic design.
So far, we've seen really innovative designs for spacecraft solar arrays and thrusters. Another component that needs to be addressed for space missions is battery life and advanced fuel cell technology. Here at NASA Glenn, teams of researchers are working on next-generation batteries and fuel cells for the Advanced Space Power Systems project. The hope is that the work they are doing will revolutionize the types of batteries and fuel cells that are currently being used for space missions.
What we're doing is developing advanced technologies for power systems that will enable future missions, space missions for NASA. Power is obviously a very important aspect for any NASA mission. So it's critically important that for deep space exploration, for instance, where we have very long-term missions, that we have very reliable systems, lightweight, low maintenance systems. So we're currently focusing on developing advanced fuel cell technology and advanced batteries. Batteries are useful for relatively low power, short duration needs, for instance, for extravehicular activity, EVA activities. And fuel cells are of value for higher power, longer duration needs, exceeding 1 kilowatt. Examples would be for rovers that may go out on extended missions, as well as surface systems that would provide power to habitats and tools that the astronauts would need in executing their mission, as well as landers to provide power after landing of the system, scavenging propellants, hydrogen and oxygen from the tanks and producing power for the surface operations.
Without getting too technical, a fuel cell is an electrochemical energy conversion device. It converts the chemicals, hydrogen and oxygen, into water, and in the process it produces electricity. In space applications, it could power any number of devices, including rovers. Because there is a need for lighter and more efficient fuel cells, the team has completely reworked older model fuel cells and produced much more efficient systems. The other electrochemical device that we are all familiar with is the battery. A major difference between a battery and a fuel cell is that a battery has all of its chemicals stored inside, and it converts those chemicals into electricity. The downside is that a battery eventually goes dead, and you either throw it away or recharge it. With a fuel cell, chemicals constantly flow into the cell. It never goes dead. As long as there is a flow of chemicals into the cell, the electricity flows out of the cell. Most fuel cells in use today use hydrogen and oxygen as the chemicals. Because batteries are so important in spaceflight, especially for EVAs or spacewalks, there is a need to dramatically increase the length that the batteries will last. Much of the work in this lab will do just that.
What our main goal is to make batteries better, make them lighter, make them safer, but provide more energy with them as well. So a lot of what we do here focuses on low-level research. What goes into the battery, not the battery itself, the different materials that go into them. And there are main components that go into a battery cell. There's an anode, a cathode, each of them made of a different material. There's a separator, and there's an electrolyte. So we do a little bit of work dabbling in each of those materials to improve how they function and then how they function together.
This work has paid off. These new batteries will soon be going on for further tests into next-gen spacesuits for final validation. And because NASA is owned by the American public, much of the technology being developed today for spaceflight may soon be showing up in devices back here on Earth. As you can see, power and propulsion will be cornerstone elements to future NASA missions. And with each passing day, the brilliant researchers of NASA continue to increase our knowledge and understanding of our universe, moving us into the unknown of deep space, while enhancing all of our lives back here on Earth.